So OpenAI just bought Windsurf for $3 billion. This is the biggest acquisition the company's ever made, and it makes perfect sense. 92% of programmers report using AI at some point in their career to help them write software, and this is the thing that's generating the most amount of tokens for the models. That's how they make all their money. The more tokens go in, the more tokens go out. That's the more money for OpenAI. That's what Windsurf is. Windsurf is a code generation assistant, a text editor plus ChatGPT. You combine these two things together, and every programmer on the planet is now 100 times faster now. I'm a developer, and I didn't even know that. Actually, I still don't know that. Because there's a 41% increase in the rate of bugs that these things produce. This is a study by UpLevel. They followed 800 developers, and they found a 41% increase in bug rate after people started using AI code generation tools, specifically Copilot. These are all Copilot studies because Windsurf didn't have the users at the time. And here's another one by GitClear, 150 million lines of code analyzed on GitHub, and a 39% increase in churn. That is throwaway code. That is code that was rewritten in 2 weeks. The definition this study uses was code that was rewritten 2 weeks later. 39% increase in code that is basically worthless. And another study that followed around almost 5,000 programmers at Microsoft, Accenture, and another Fortune 100 company that chose to remain anonymous, found that for junior developers, basically if you wanted to go from a 0.1x developer to a 1x developer, it was actually kind of helpful, like a 26% improvement, something like that. And with senior developers, if you want to go from a 1x to a 10x developer, they found no statistically significant improvement whatsoever. This is not making people 100 times faster. Actually, senior developers at real established projects at real companies, when we're tracking with real studies using real data, don't see any statistical improvement in productivity by any metric. They're actually just seeing more negative metrics. So this stuff is like not working. And that's the thing. This stuff doesn't work. And Dijkstra saw this coming. He actually saw this before he died, before LLMs were ever made. He died in 2012. 5 years before the transformer was invented. And he already wrote about it. He was already, complaining about natural language programming and how it's never going to work. Because even though he couldn't see LLMs coming, he knew that people were talking about this in programming. They were talking about how great would it be if we could just program with natural language. And what he talked about is Greek mathematicians in ancient Greece were the first people to start talking about this. They're like, well, math is terrible. There's all these symbols involved. It's like so structured. It's so like rigid. I have to do like all this like arithmetic and moving of parentheses. Like this stuff is like not helpful for me. So I just want to use natural language, and I'm going to go 100 times faster, right? And what happened was that there was no progress whatsoever. There was a mathematical and scientific dark age. Nothing happened. Nothing moved forward. I mean, zero. It was just zilch. And then the Western European mathematicians brought the symbols back, and then math picked up again, and then it started working. And this is also how we get large language models in the first place. This is how we get AI. This is how we got the computer, the internet. This is how we get the languages. It was formalized structures, formalized symbols. They're so powerful. The entire transformer model that OpenAI is built upon. This is what ChatGPT is. It is a general pre-chain transformer. That's what it stands for. And this is linear algebra. And how is this model able to take in so much information and calibrate it and train itself? It takes in, what was I supposed to say? What did I actually say? What is the difference? Okay, that's my error. And then what do we do with that? We use calculus. We use the chain rule. And that's how we are able to tune these models. That's why they're so superhuman in their performance. It was all due to math. And this is what we have to do. Because this approach, what happens when you're not able to formalize things and when you're just like not using any kind of structured approach, no scientific methodology, what happens is you just take two things that are right in front of you. There's like, oh, editor, ChatGPT. I'm using ChatGPT in my browser. I'm using editor here. I'm gonna go plug them together. And then you go and tell everyone it's 100x revolutionary improvement. It is not. It is clearly not. We're seeing in the data all over the place that it's just not working. And ChatGPT can really like solve these like 50 line of code problems. It can solve like leet code problems. It can solve test answers. It's like 28% accurate in leet code problems. I don't know when this benchmark was made, but it's probably better now. It gets incrementally better. And I'm not saying it's not good. I'm not saying that it's not helpful that the AI can write code so fast. In fact, that's what we do. We do code generation. So I'm using the stuff every day. I'm not saying that it's like worthless. I'm just saying if you just take text editor plus ChatGPT and plug them together, that's not inventing anything. That's not progress. And you can see that in the data. You can see evidence that this stuff doesn't work. You have to think about it from a structured first principles perspective. When you have this like really, really powerful thing that's brand new, that is a completely game changer, you have to go back to first principles thinking and think like, okay, like I had these constraints before and I have these constraints now. And now I need to go and think about all the possibilities of like, what can I do with this thing? And I need to find the maximally optimal or efficient way to use this stuff. And if you're just like not formalizing things, if you're not thinking in a structured, methodical way, that's what happens. You just see like two things and you just plug them together. That's not going to get you anywhere. It has never got anyone anywhere if they're not formalizing things. So we need to be building abstractions. This is how all science happens. This is how you strategize. This is how you problem solve. You problem solve with abstractions. And abstracting is all about drawing things away. It's all about hiding details. If I am a hunter and I am trying to tell my friends, hey, there are deer in a prairie, I don't need all the information in the universe to tell them that. I don't need to physically take them to the prairie and show them that there's deer there. I could just draw a picture, like, hey, there's 4 deer here, and this little guy, I don't know what he is, but who cares? Let's get spears and arrows, and let's go hunt them and get food. It'll be great. They're that way. That's all you need to know. No information necessary, and this is a strategy. We can plan about it days in advance. We don't have to spend all this time just trudging. And this is how all mathematics happens, all science happens. This is what an abstraction is. And a really simplistic way to think about this is you're just taking a lot of information from one place and you're only looking at small parts of it. You're reducing the amount of information that you're thinking about, and that's abstracting. So this is the greatest page on the internet. Go to Wikipedia, go to algebraic structure. This is a game changer for your ability to problem solve. And this is the reason why Dijkstra was able to foresee that people would try to do natural language programming in this way and get nowhere, and get absolutely nowhere. Because this is old stuff. It's thousands of years old. It's like ancient Greek. This stuff dates back so long. And this is how Einstein solved problems. This is how Newton solved problems. This is how Galileo solved problems. This is how we got information theory, computing, the internet. It's all about the algebraic structures. So if you cannot find your solution in this list, if you're not thinking about your solution in this list, what does that mean? That means you're looking at 2 things right in front of you. That means that you're the guy who's taking your friends to the prairie and saying, hey, there's deer there. You're not the guy drawing the cave painting. You're not strategizing. You are not thinking about the solution space. And you're not thinking about the constraints and all the possibilities. You're not trying to find the best solution in those possibilities. You're only thinking about what's right in front of you. Those are the only solutions you can think about when you can't formalize things. And this is kind of like also something where like great intuition comes from. Great insights just drop out of this stuff. That's why there's such revolutionary leaps and why they're such game changers. Because people thought about Einstein and Feynman and these guys as really intuitive people. Like Einstein, they talked about him like moving his hands and visualizing things in his head when he was thinking about the theory of relativity. And Feynman was like had these great intuitive explanations. They called him the great explainer. But they did this sort of sleight of hand that no one really knows about, which is that these guys are both great calculators. They are very, very good at one fundamental skill, and all of the people that made real progress are good at one fundamental skill. They can take a lot of the complicated world out here and they can project it into a little simple box down here, and they can manipulate the simple box. They can model things. And they model things specifically in an algebraic way, in a very formalized, structured way. And once you do this more and more and more, it becomes more intuitive. It just becomes second nature, and you're not thinking about it. Like it's not the constraint you think it is. And that's the mistake people have been making for thousands of years. It just keeps happening. It's that people look at formalizing systems and formalized critical thinking and problem solving as a barrier or a burden. They think of it as like this weight that they have to hold. And they just want to like think about things like with natural language in their native tongue. And that just doesn't work. Because your native tongue, it can solve problems, but all it can do is it could just think like, oh, there's this and that, and it's like all this stuff right in front of me. Like that's what our waking mind is doing. And it's not really able to critically think ahead unless you start using tools that let you do that kind of stuff. And so we actually did this with code generation. We thought about code generation from first principles thinking. Like I said, I like code generation. I don't think it's not a bad thing that AI can write code 10,000 times faster than me. Like, I don't think that's a bad thing at all. I do think Windsurf, AI plus ChatGPT plus text editor, I don't think that that's getting anywhere. I don't think that's helping anything. I don't think it's productive. They'll make iterative improvements. Like, maybe you'll see like a 20%. People figure out a way to make it work, right? They'll figure out a way to square the circle. That's fine. People are they're very good at optimizing things just naturally. And I get that. But I'm just talking about like a real strategy, a real paradigm shift. Like thinking we have this LLM and it can do all these amazing capabilities that are like superhuman. It can think about all the syntax in the world, all the documentation in the world. I can feed it documentation live in like milliseconds. It could just read things instantly. And it's superhuman. It has like really, really strong leverage. Like, how do we use that leverage? And what are the constraints of the LLM? So you got to think about the constraints of the problem space when you're trying to figure out like a real paradigm shift or a real revolutionary leap in productivity. And the way you get to a real leap in productivity is the same way everyone else does. It's always been the same for thousands of years. You have to think about common properties, and you have to think about like a simple set of objects or like a simple representation or a simple model for the problem of AI plus code. How does AI and code interact? And you have to form a theory about it, a structured formal theory and a structured algebra. That is the only way to do critical thinking. It's the only way to problem solve. Every great designer in the world does it this way. And you would be amazed at the insights that fall out once you start doing this stuff. Like, you're just kind of thinking like one step at a time, and you're doing this sort of algebraic stuff, and then inferences happen. Then you start with theorems, then you start finding laws, and you start figuring out like all these crazy inferences about stuff that you could talk about the whole universe universally, and then you start noticing things, and you look like a genius because you're like, oh, 3 plus x minus 3, like that works for all x's. That's just x, and insights happen. But you don't think of the insights. The insights just like appear in front of you when you're like doing the calculation. That's what Feynman did. Like, that's literally just calculating things, and then insane insights come out. And what insights did I find when I was doing code generation from first principles thinking? I decided to model things in the simplest model I possibly could. What is the most complicated thing about the code generation, right? It's the code. So I came up with these code tables. There's a name, a description, I have columns and I have rows, and they have inputs. So it's a code table. It's inputs and columns, basically. And the code is completely abstracted. That is like the best possible thing to abstract, right? And the problem with code bases is that there's so much code in them. If there's like 15 million lines or 100 million lines of code, there's so much freaking code in these things. It's like the biggest problem with these. Like, what if they just what if I didn't have to feed all that code in the model? And turns out you don't. I just don't care. My system, RAI, does not look at the code. It doesn't need to look at the code because the code has been abstracted. And we think about the properties of code tables. They're transitive, right? Okay, so if like code table A feeds into B, feeds into C, if code table A breaks, does C break? Yeah, because it fed into each other. They're inputs. That's called a transitive property. And so as you start modeling things like this, you start noticing inferences, you start making these insights, and it seems so counterintuitive. Like, when would Windsurf actually think, oh, we should just like hide the code? How do we hide the code? How do we abstract the code away? Then we could scale to like 100 million lines or a billion lines or a trillion. It scales forever because it doesn't need to think about the code. It can just think about like, oh, there's 2 tables, plug into that table. And it's like this really small amount of information for it to pay attention to. And for me to pay attention to. I don't read the code. There's a code tab on my app. It's right there. I don't look at it. I never click on the code tab. I don't need to read the code tab because I just look like, oh, is that the PDF files in the input folder? I just go in my input folder. I'm like, oh yeah, that's the files. Great, we're done. No more. It's easy. Like, I just like solved the problem. And this was, the whole thing was just solved by abstraction. Abstraction's the core thing here. You have to take the code, and it's blurred here. I did that because the code is proprietary, but also it makes a perfectly good point. So it's actually like really convenient. You blur the code, blur things. This is how you do problem solving. You have to hide details. And so I'm hiding the code, and the code might as well be blurred all the time because I'm never reading it. I don't care about the code. All I care about is the data. Oh, are those the JSON files? Yeah, they look like the JSON files to me. I can go in this folder and I can go check. Yeah, that's the JSON files. Cool. And what's the inputs of this table? This one feeds in from that one. That one feeds in from this one. Cool. That's all I need to know. All of these code tables, they have so much code inside of them, but I don't care. And the AI doesn't care. No one cares anymore. We know the code's correct. And so the code goes into a black box and there's a barrier and it says, do not cross. Never cross. You never read the code. It's just, you just don't let yourself do it. And this is how you do crazy problem solving. This is how you get algebra. Like, for me to do 3 plus x minus 3 equals x, I can never look at x. There has to be an abstraction barrier. If I want to say this works for all possible x's in the universe, and this will always be true forever, I can't look at x. Like, the abstraction is the important thing. Like, it's so critical that I don't know what x is to be able to actually solve problems. That's the whole essence of critical thinking. This is the whole essence of problem solving. And humans have been building abstractions for thousands of years. If you really want to solve problems, if you really want to optimize things, you gotta learn this skill. If you're interested in this video, please subscribe. Also, I have a newsletter that goes way deeper, The Automated Founder. Please check that out if you want to think about these concepts more deeply, if you want to learn some of the things that we use to be able to solve really, really complicated problems like code gen, and the reason why we're actually able to do these things end to end, remarkably cheaper, 100 times cheaper. Please check out the newsletter. Thank you so much.